to the next lecture in Module 3 on finite difference method. We will continue from where we left in the first lecture on second order derivative. So we are going to focus on finite difference approximation of second order derivatives in this lecture. What we discussed in lecture 3, so previous lecture was we discussed approximation approaches and we derived approximations based on Taylor series expansion for finite difference approximation of second order derivative. So we are going to continue the same part, that is we would derive finite difference approximation of second order derivatives. We will continue our approximations based on Taylor series expansion, particularly the one based on general procedure on uniform grids. Then we will take up how do we obtain finite difference approximations based on polynomial fitting, and then we would try and obtain approximation of second order derivative in a scalar transport equation. So now let's have a relook at our general procedure which we outlined earlier, that on a uniform grid difference approximation for second order derivative can be expressed as del 2 f over del x square I is approximately equal to a times fi plus b times fi minus 1 plus c times fi plus 1 plus d times fi minus 2 plus e times fi plus 2 so on divided by delta x square. And these coefficients a, b, c, d can be determined from Taylor series expansions for the function values fi, fi minus 1, fi plus 1 and so on. We will substitute them on the right hand side and try and equate the terms appearing on both the sides, and thereafter we will get a system of equations from which we can determine a, b, c, d, etc. Let us take one or two examples of this approach which was proposed by Chung in 2010. Now first thing we will take up is 3-point central difference formula. So this is our general formula, del 2 f over del x square I is equal to a fi plus b fi minus 1 plus c fi plus 1 divided by delta x square. And using this formula, let us find out the values of a, b and c involved in this approximation using Taylor series expansion. So we want to find out a 3-point central difference approximation or central difference scheme for second order derivative. Okay, and the grid is supposed to be uniform, and let us use symbol delta x to denote our grid size. So let us rewrite our formula of Chung, del 2 f over del x square at the grid point I is approximately equal to a fi plus b fi minus 1 plus c fi plus 1 divided by delta x square. So basically what we have is we have taken 2 points in the neighborhood of our grid point I. So grid point I, we have taken the grid point I plus 1 to the right of it and grid point I minus 1 to the left of it. Now let us substitute in this formula the values of fi minus 1 and fi plus 1 using Taylor series expansion around point xi. So if you do that, let's have a look at the numerator. That's AFI plus BFI minus 1 plus CFI plus 1. The first term remains as such, AFI. Now for B times for Fi minus 1, now let us use Taylor series expansion. So it will be Fi minus delta x times del f over del x at I plus delta x square by 2 del 2f over del x square at I minus delta x cube by 6 del 3f over del x cube at I plus delta x to the power 24 del 4f over del x 4 plus other higher order terms. So this completes our expansion for our value of Fi minus 1 in terms of Fi. Add to it now C times the expansion for Fi plus 1. This becomes Fi plus delta x times del f over del x I plus delta x square by 2 del 2f over del x square I plus del x cube by 6 del cube f over del x cube I and plus other higher order terms. Now let us collect the like terms, like the ones which involve function values or the first derivative, second derivative and so on. Let us collect them together. So we have got three terms involving function values, A Fi, B into Fi and C into Fi. So we will get A plus B plus C times Fi. Now let's next collect the multipliers of the first derivative. So we get minus B coming from the expansion of Fi minus 1 and C minus B plus C times delta x del f over del x I plus delta x square by 2 B plus C del 2f over del x square at I plus delta x cube divided by 6 within brackets we will get minus B plus C del cube f over del x cube at I plus delta x to the power 4 by 24 B plus C del 4f over del x4 at I plus higher order terms. So now let us substitute this value which we have obtained for AFI plus BFI minus 1 plus CFI plus 1 into our generic formula which we have started off with. Let us call this equation 1, the expansion which we got as 2. Substitute into equation 1. So what we will get? Del 2f over del x square. That's what we get on the right hand side. This is equal to a plus b plus c divided by delta x square times f of I plus minus b plus c divided by delta x del f over del x I plus b plus c by 2 del 2f over del x square at I plus delta x by 6 minus b plus c del cube f over del x cube of I plus delta x square divided by 24 b plus c del 4f over del x4 of I plus higher order terms. So now let's compare the coefficients of the function values, derivatives of different orders, which we have got on the left hand side and right hand side. So on the left hand side we don't have any term which contains fi. We don't have any term containing first derivative or third derivative and so on. So if we compare the coefficients on two sides, we can clearly say, so comparing the coefficients on two sides of terms involving fi del f over del x of I del 2f over del x square of I and so on. What do we get? We get a plus b plus c is equal to 0. That's what we get, the coefficient of fi. On the left hand side there is no term on fi, so its coefficient is 0. On the right hand side we got a plus b plus c divided by x square, so this should be set to 0. So we get this equation in terms of a, b and c. A plus b plus c is equal to 0. Similarly, there is no term which contains the first derivative on the left hand side, and but we have got one term minus b plus c divided by delta x del f by del xi on the right hand side, so its coefficient must vanish as well. So we get minus b plus c is equal to 0. We got three unknowns, we need one more equation. So now let's compare the coefficients of the second derivative. The coefficient of second derivative del 2f over del x square I is 1 on the left hand side. Its coefficient on the right hand side is b plus c by 2. So if we equate these two, we get b plus c is equal to 2. From these equations, if we just add the last two equations, we get 2c is equal to 2, which implies c is equal to 1, and we can solve for b from second equation. B is equal to c, so we get b is equal to c is equal to 1. Substitute these values of b and c in the first equation. So this equation will give us the value of a is equal to minus b minus c, so thereby we get value of minus 2. So let's summarize it on the slide. So by Taylor series expansion we have got A is equal to -2, B is equal to C is equal to 1. So therefore we get a pretty simple form for the second order derivative. Del 2f over del x square I is equal to f of I plus 1 plus f I minus 1 minus twice of f I divided by delta x square. What happens to a truncation error? So truncation error, let's see on the right hand side the terms which involve the higher order derivatives. The term containing the third derivative has got minus b plus c. B and c are equal, so this term vanishes. So our truncation error is basically delta x square divided by 12. We substitute for b and c here. So b plus c we get 2, 2 by 24, that gives us 12. So delta x square by 12 del 4f over del x 4. So we can clearly say that this central difference approximation has got a truncation error of the order 2 over x square, that is, it is a second order accurate scheme. We can also find out a one-sided formula, a 3-point backward difference formula by taking the values at point fi, fi minus 1 and fi minus 2, and in this case our truncation error involves the terms of order delta x. So this 3-point one-sided difference formula, which we can get using this general procedure, has got a first order accuracy. We can also obtain higher than second order formula using this Taylor series expansion. So let's take a 5-point central difference formula. We will do part of it, part of the derivation, and part will be left to you as an exercise. Okay, so we want to find out a 5-point central difference formula for second order derivative. This higher order formula is sometimes used in the finite difference codes which require extremely accurate finite difference approximations. So our first point would be our central point, that ith grid point. We will take 2 points on each side, that is grid point I plus 1 and I plus 2 on the right hand side of point I, and I minus 1 and I minus 2 to the left. So our difference scheme or difference formula we can express as A f of I plus b times f of I minus 1 plus c times f of I plus 1 plus d times f of I minus 2 plus e times f of I plus 2 divided by delta x square. So we have got 5 unknown coefficients which we must determine using Taylor series expansion, and let us do that straight away by putting expanded forms for fi minus 1, fi plus 1, fi minus 2 and fi plus 2 on the right hand side. So we can write 1 over delta x square And now let us try and collect similar terms, the terms which are going to multiply Fi. Well, we will get a term Fi in all these remaining 4 expansions. We get Fi would be multiplied by A plus B plus C plus D plus E. Now next we will have the terms containing, let us say, coefficient of del f over del x I. So what do we get? The first term AFI, that as that will remain as such, we will get this del f by del xi occurring in the expansions of fi minus 1, fi plus 1, fi minus 2 and fi plus 2. So let us take, what do we get from expansion of fi minus 1? From here we will get simply a term containing delta x. So here we will have, let us take delta x common. So from expansion of fi minus 1 we will get the contribution minus b. From expansion of fi plus 1 we have the coefficient delta x into c, delta x we have taken out, so we get plus c. Fi minus 2, now here the difference is minus 2 delta x, so we get minus 2 d, and similarly the contribution coming from expansion of fi plus 2 would be 2e. So that completes our collection of the terms from expansion which have del f over del xi into them. Next let us collect the terms containing second order derivative del 2f over del x square at I. Let us take this delta x square by 2 outside. So from expansion of fi minus 1 we will simply get plus b. From second fi plus 1 expansion we get the contribution c. From fi minus 2 and fi plus 2 we have got 2 delta x whole square. So here we will get 4d plus 4e. Next, the third order derivative, here let us take delta x cube by 6 outside. So we get from expansion of fi minus 1 the contribution would be minus b, from fi plus 1 plus c. From fi minus 2 we will get 2 cube into d, that is 8d, from fi plus 2 8e. Similarly del cube f over del x to the power 4i. Let us take del x to the power 4 divided by 4 factorial, that is 24 outside. So we would be left with b plus c plus 16d plus 16e. Next, our fifth order derivative del 5f over del x5 delta x5 to the power divided by 120 is taken as common. So we get minus b plus c minus 32d minus plus 32e. Let's write one more term, del 6f over del x6 of fi common multiplier del x to the power 6 divided by 720 b plus c plus 64d plus 64e and plus remaining higher order terms. Now, to obtain the equations for a, b, c, d, e, now let us compare the terms on the LHS and RHS of this equation. So, on left hand side we have got only the second order derivative term. So, coefficients of rest of the terms in the function value itself or first order derivative, third order derivative, fourth order, fifth order and so on, they can be all set to 0. So, we need 5 equations. First let us compare the coefficients of fi on both the sides. So, this gives us a plus b plus c plus d plus e is equal to 0. Let us call this equation as 1. The second equation we can get by comparing the coefficient of del f by del xi in both LHS and RHS. On LHS we have got value 0. So, on RHS we will get minus b plus c minus 2d plus 2e is equal to 0. Next, compare the coefficients of del 2f over del x square. So, this will give us b plus c plus 4d plus 4e is equal to 2. So, now got 3 equations. We need 2 more. So, let's next compare the coefficient of del cube f over del x cube I at both the sides. So, we get minus b plus c minus 8d plus 8e is equal to 0. And next equation we can get by comparing coefficient of del 4f by del x4. So, that gives us b plus c plus 16d plus 16e is equal to 0. So, now we got 5 equations in 5 unknowns a, b, c, d, e, and you can solve these equations. That I would leave as an exercise. I will just give you the summary of the results, that if you solve these equations, what do we get? We will get the values of a, b, c, d, e. So, we get, on solving these equations, we get a is equal to minus 5 by 2, b is equal to c is equal to b and c, they are both equal, we get 4 by 3. Similarly, d and e are also equal, d is equal to e equal to minus 1 by 12. We can substitute these values and you can make few observations. By substituting the value we get the final formula, and the values of d and e are equal. So, that will tell us that the coefficients or the coefficients which multiplies del 5f over del x5, that becomes 0. Okay. So, the leading coefficient in truncation error would be given by the multiplier of del 6f over del x6. So, truncation error for this scheme, that is del 6f over del x6I b plus c plus 64d plus 64e times delta x to the power 4 divided by 720. Substitute the values of b, c, d E and so on to get the actual value of the truncation error. You can clearly see this order of truncation error is delta x to the power 4. So now let's have a look at the summary of this formula which we derived. This 5-point difference formula, del 2 f over del x square I is equal to minus 30 fi plus 16 times fi minus 1 plus fi plus 1 minus f of I minus 2 plus f of I plus 2 divided by 12x square, and the truncation error is of the order delta x to the power 4. So this scheme is 4th order accurate. So now here we would put a stop to our approach or derivations based on Taylor series expansion. Let's have a look at the next scheme, that is obtaining approximation of derivatives by polynomial fitting. We have already seen this expansion earlier, that a generic function fx can be approximated by a polynomial as fx is equal to a0 plus a1 into x minus xi plus a2 times x minus xi square plus so on an x minus xi to the power n. We have taken it in terms of x minus xi so that we can easily obtain the expression for the derivative at x is equal to xi. And these coefficients a0, a1 and so on, we would obtain by fitting the interpolation curve which is given by this polynomial to the function values at appropriate number of points. And if you want to find out derivatives, just simply differentiate this polynomial. So we get del f by del x is this coefficient a1. The second order derivative at xi is given by 2 times a2. Third order derivative del cube f over del x cube is given by 6 times a3 and so on. So we already used this approach to derive few formulae for first order derivative. Now let's try and do one more and one derivation for our second order derivative. In fact, as a part of derivation we can also obtain a formula or higher order formula for first order derivative as well. So what we would try to attempt is, let's find out a 5-point finite difference approximation, okay, by fitting a 4th degree polynomial. So 4th degree polynomial is given by fx is a0 plus a1 times x minus xi plus a2 times x minus xi square plus a3 times x minus xi cube plus a4 times x minus xi to the power 4. So in this 4th order polynomial we have got a0, a1, a2, a3 and a4. We have got a total of 5 unknown numerical coefficients. So that is why we need to equate this polynomial at 5 grid points to determine the values of a0, a1, a2 and so on. For a central difference formula, let us take the grid points as I minus 2, I minus 1, I plus 1 and I plus. Now let us get back to the board and try to derive our approximation based on 4th order polynomial fit. So polynomial fitting approach. First let us note down our grid points I plus 1, I plus 2, I minus 1 and I minus 2. For the sake of simplicity of derivation, let us assume a uniform grid. So let us take a uniform grid and our grid spacing is delta x. So with reference to point I, the spacing between I and I plus 1, this would be delta x, Similarly, the difference between I and I plus 2, that would become 2 delta x, and so on. So, if we choose our coordinate frame centered at the grid location xi, we can obtain the values of the coordinate differences for the different points for substitution in our polynomial. Now, let us write our fourth order polynomial fit. Polynomial interpolation for function fx. So, fx is equal to a0 plus a1 times x minus xi plus a2 times x minus xi squared plus a3 times x minus xi cube plus a4 times x minus xi to the power 4. So, I have taken a fourth order polynomial. Now, let us equate this interpolation to the function values at points I plus 1, I minus 1, I plus 2 and I minus 2. So, let us do it one by one. First, by equating the function values at point xi, fxi is given by fi, and that gives us a0. So, we straightway we have got the value for a0, which we can substitute in further expressions. Now, f of I plus 1, that will give us fi plus 1. Fi plus 1 is equal to fi plus a1 times delta x plus a2 times delta x square, because difference between xi plus 1 and xi is simply delta x, plus a3 times delta x cube plus a4 times delta x4. So, interpolation is equation 1, 2, let's call this equation as 3. Function value at I minus 1, fi minus 1, this will be equal to fi. Now, x minus xi minus 1, sorry, x minus xi, now x is xi minus 1. So, xi minus 1 minus xi, that will give us minus delta x. So, we get a1 times minus delta x, this minus sign comes here, plus a2 times minus delta x square, which simply gives us plus delta x square minus a3 times delta x cube plus a4 times delta x4. Let's call this equation as 4. Next, equate the values at point I plus 2. So, f of I plus 2 is equal to fi plus 2 delta x times a1. Now, if you got 2 delta x as the x minus xi, so the square term would give us 4 delta x square times a2 plus 8 delta x cube times a3 plus 16 delta x4 times a4. Let's call this equation as 5. F of I minus 2, this will be fi. Now, x minus xi in this case would become minus 2 delta x. So fi minus 2 delta x times a1 plus 4 delta x square times a2 plus 8 delta x cube, sorry, we have taken cube of minus 2 delta x, so that becomes minus 8 delta x cube times a3 plus 64 delta x4 times a4. Let's call this equation as 6. Now we have got the required number of equations. Equation 2 gives us the value of coefficient a0. We are interested in finding out the values of coefficients a1 and a2. a2 will give us the second derivative and a1 will give us the approximation for first order derivative. Now let's have a look at equations 5 and 6. Let's add them together. So add equation 5 and equation 6. So what do we get? F of I plus 2 plus f I minus 2 is equal to 2fi. See, this a1 and a3, these two terms would vanish. So we get 4 and 4, 8 delta x square times a2 plus 32 delta x to the power 4 times a4. Similarly, if we add equations 3 and 4, the ones in terms of fi plus 1 and fi minus 1, let's call this equation 7. So add equations 3 and 4. So this addition will again eliminate a1 and a3 terms. So we get another equation in terms of a2 and a4. So we will get f of I plus 1 plus f of I minus 1 will be equal to twice of fi plus 2 delta x square times a2 plus 2 delta x to the power 4 times a4. So now the 7 and 8, these two equations involve only coefficients a2 and a4. So we can eliminate a4 and thereby obtain a value for a2. So to eliminate a4, let's multiply equation 8 by 16. So equation 8 into 16, that will give us 16 times f of I plus 1 plus f of I minus 1 is equal to 32 fi plus 32 delta x square a2 plus 32 delta x to the power 4 a4. Okay, now let's subtract equation 7 from equation 9. So 9 minus 7. If you do that, we would be able to eliminate a4. Okay, so we get 16 of fi plus 1 plus f of I minus 1. This is equal to 30 fi plus 24 delta x square a2, and from here now, sorry, and on the left hand side we will have it in another term minus of f I plus 2 plus f of I minus 2. So now let's rearrange and let's write down value of 2a2. So 2a2 will become 16 of f I plus 1 plus f I minus 1 minus f I plus 2 plus f I minus 2 minus 30 f I divided by 12 delta x square, and that's what we were looking for, because twice of a2 gives us the second derivative. So that is del 2f over del x square at I. Now we have got an approximation for it. Now let's write the terms in index order. So we get minus f of I minus 2 plus 16 f I minus 1 plus f of I plus 1 minus 30 f I minus f of I minus 2 divided by 12 delta x square. Okay, so now let's summarize this result on our slide. So that's what we get. Del 2f by del x squared I is equal to twice of a2, which is minus fi minus 2 plus 16 of fi minus 1 minus 30 times fi plus 16 times f of I plus 1 minus f of I plus 2 divided by 12 delta x square. Now these equations which we had derived, or which we have written for these coefficients a1, a2, a3 and a4, you can also find out, and that I would leave as an exercise. So this is an exercise. Solve the preceding equations for a1, and if you solve for a1, that is an approximation for del f over del x I. So this is one exercise. Okay, and the second exercise which I would like you to do is find out truncation error for the approximations which we have obtained for del f over del x I and del 2f over del x squared I. Okay. Use Taylor series expansions to find out your results. Now there is something which I would like to note here, which you can try and verify from your results on truncation error. We have already made similar comments on the approximation of first order derivative by polynomial fitting. So what happens in the case of second order derivatives? In general, truncation error of the approximation to second order derivative obtained by fitting a polynomial of degree n is of order n minus 1. However, one order is gained, that is truncation error is of order n if grid spacing is uniform, this first condition, and an even order polynomial is used. So in just discussed example, we had taken uniform grid spacing and polynomial of order 4. So this observation says that your truncation error should be of order 4. Now please verify from your derivations. Today in this lecture we stop here as far as approximation of second order derivatives is concerned, and in the next lecture we will have further look at finite difference approximations for the second order derivative occurring in generic transport equation and for mixed derivatives. We will also take up the case of multidimensional problems. So, how do we obtain the approximation for the derivatives occurring in the partial differential equations in 2 and 3 dimensions, and thereafter we will take up few applications in the next lectures.